collections. So we discussed collections when we were discussing SDC, and there are all these nice type of collection commands. Get ports will return all the ports. Get clocks will return all the clocks in our design. All inputs will return all the inputs to input ports. All registers will return all the registers. However, these things all return what are called collections, and a collection is not a normal Tickle string. It's a special type of a database unit that has all kinds of properties and so forth. It actually returns a pointer or a handler, just some sort of a number in hexa that is whatever the collection is. So when we want to do things on it, we have to use special commands. Like, for example, to see the length of a collection, we can't use a length. We have to use size of collection. To iterate, we can't use for each. We have to use for each in collection. To get the name of a string or an object, because the name is just this pointer, this kind of number, instead of that, we have to do get object name and figure out what the name of this is. Okay, so these are things that can be used and are often used, and we kind of use them once in a while and sometimes don't. But collections, they're not actually native to the Cadence tools. In fact, they were developed as part of the Synopsys design constraints. What Common UI introduced is something called a DPO, a dual port object, which is something that says the object type and then its name. They're very confusing, actually. It takes a long time to get used to them, but they're much more powerful within Cadence tools. So going back to our discussion of the different types of get commands and the getDB, setDB. So the collections, like the SDC type collections versus the Cadence database common UI type of syntax, I'm going to show you some examples of that. So we already saw get ports, which is going to return all of our ports, but there are many more of these get things, and you can push tab and see a lot of them. But for example, get cells is going to show me all of the cells I have currently in my design. Get clocks is going to show me it doesn't have anything actually, because we didn't read in our SDC. We'll see that after we do init design. But there is get nets and get pins and get and so forth. But okay, when I did my get ports, okay, I also have the shortcuts kind of to get specific things. So I can do something like all inputs. Okay, it shows me all the ports that are inputs, which are clock, reset, act, and up, down, n. I can do all outputs, which are, the counts and the overflow. And I can do things like all registers. And that's going to give me all of the registers in my design. So the thing is that if we see here, when I write one of these commands, I get this OX something. And that's like a file handler or a collection handler or a pointer, some sort of a pointer type of a thing. And it is not an actual string. So I'm not getting this list as a string. Remember, everything in Tickle is a string. I'm getting a pointer. So if I want to do something like, I'll write like for each, inp, and then I'll do something like all inputs, and then I'll write puts $imp. What is going to happen, do you think? Well, if you think about it, what it's going to get is going to show me OX12. Why did that happen? Because when I ran all inputs, it returned me a collection, which is actually just this handler or this pointer that's called OX12. And when I went and for each, I went over all of the list members, it only returned that thing. But what I wanted to do actually was to go over all of the inputs that are over here, which there are several of them. So what I should have written is actually not for each, but for each in collection, and then let's see what happens. So it again goes and gives me all kinds of file handlers, and that's because now there are 4 of them instead of 1, but I still don't want to know what to do with that. So if I want to see what those actually are, I will have to go and do something like this. So I have to write get object name, and then Let's see if that worked, and it does. It gives me clock, reset, and act, and up, down. So this is kind of a not nice thing about the collections, that they're just this handler, and then I have to go and evaluate them with something like get object name to see what's happening over there. So that, and I have to use for each in collection before for each. It's not just a simple tickle list. So for example, if I do something like L length, to see what the list length of all inputs, what I'm going to get here is I'm going to get 1. But so if I want to find the actual length of the all inputs, what I have to do is size of collection to all inputs, and that will give me the size 4. So remember that these are collections, and they are not just standard tickle lists. So let's look at these DPOs to navigate the Genus database. So the Stylus Common UI, which was developed several years ago, it provides a unified database across all the digital implementation tools, Genus, Innovus, Tempus, Voltus, etc. And that's really nice because now we can use the same commands and the same structure to access all of our tools and write the scripts very similarly. And we'll be doing that throughout these tutorials. So the database access is completely done through this getDB and setDB commands. So getDB, the object, and then dot and the attribute name, or setDB object dot the attribute name and the value we want to change. Okay, so they work with these dual port objects. The dual port objects are tickle strings. So they are not like collections, which are like a pointer or a handler. They're actual strings, and then we can do things with them. Just as an example, to get a list of ports, we'll do getDB ports or getDB designs dot ports. Okay, so each of these types of things that we have here, the dual port objects, they have lots of attributes. So I want to get the direction of the clock port. I do getDB, I get the name of the dual port object, which is port colon. So that's the 2 ports. One is the first one, that's the type of object, then the colon, and then the name of the object. It's going to be called SM/clock. That is the clock port of our design, which we'll find out, for example, by doing getDB ports, okay, or by opening the design browser, for example, and copying its name. Okay, and then it has lots and lots of attributes. So I can write dot, and I can press tab, and I'll get all of the optional attributes. And if I do dot direction, it's going to return in because it's an input port. Or I can do something like this. I can do like very nice things. For example, getDB ports. That's going to return all the ports. But I don't want to return all of the ports. I only want to return the inputs. So I can do -if. And that's if they have an attribute of direction that is equal to in. So that's going to filter out only the input ports from the entire list that is returned. When I look at dual port objects in contrast to collections, they do return tickle lists. So if I do something like getDB and let's say ports, which is going to give me all of the dual port objects of the port. So you see port colon SM clock. So these are the dual ports. They have this one thing which is like the type, the object, and then what its name is. That's how all of these things are. So I can then iterate over that. So let's say I'll say length, and then this getDB ports. Okay, well, it's going to give me the whole length, which is 9 in this case. Okay, or I can do for each from getDB ports, and then I can do puts $por. It's going to actually print out every single one of them on a separate line. So these are tickle lists, and they're kind of more accessible. So another really nice thing about these DPOs is that I can access all kinds of attributes, and tab completion is built into Genus and Innovus and so forth to help me with that. So first of all, we saw before that I did getDB ports, and that was kind of a simple way of accessing, but another way is using getDB design, and designs, the design is SM, that's our top level design, and the only design we have in this project. So what I can often do is I can do getDB designs and then look at the attributes, and if I write ports, I will see that that returns the port. So that's the same as writing getDB getDB ports. Okay, but what I could have done is I could have pressed tab, and you see that there are all these options that I can do there. So right, I keep pressing tab, and I'll get the getDB ports. But if I put another dot here, now it will show me the actual attributes of the ports. So if I press tab, I get all of these attributes. And for example, one of them will be direction, and then it will reply to me in, out, out. So those are the different ports and their directions. So that's a nice type of a thing to do. I can also put all kinds of conditionals in there. So for example, if I only want the input ports, what I can do is I can do getDB design.ports. Okay, minus if, and then in the minus if I do dot direction equals to in, and it will give me only the input ports. So that's the same as doing all inputs, obviously, but I can do real powerful things with that. Okay, so that's really nice. So I can take it a step further and, for example, iterate over what happens over here. So let's say I go this getDB designs.ports, and then I say for each, okay, and open a curly brace. And then I do something like puts, okay, and I do getDB $object.name is an, and I do getDB dollar object dot direction, and this should print out each of the ports and what its direction is. And we see clock is an in, reset n is an in, count 3 is an out, overflow is an out. So that way I can really script kind of cool things with that very easily. So using this minus for each, I iterated over things. Using the minus if over here, I could filter things out from the big database objects that I was returned. So the next step is the init design command. And the init design command is a super command. We'll see it later in Innovus as well. It's even a bigger command there. It kind of takes everything that we read in and it starts processing it. So we loaded the .libs, the .lefts, the netlist, and so forth. And now it's going to actually process all this stuff. Most important, it processes the SDC files. So we read the constraints as part of the MMC, but it didn't have the design objects. We didn't have all the ports and the clocks and so forth, so we couldn't actually go and process them. So now it's going to process them, and if we have any mistakes and problems with our SDC, we better find them out now. So how are we going to do that? We are going to use the check timing intent command. That's kind of a linter for timing. It finds things like combinatorial loops, multi-driven nets, unconstrained inputs and outputs, and so forth. Okay, so that is really something we have to do. We're going to have to go and debug our timing with the check timing intent command. So let's look into the SDC file over here under inputs sm.sdc, and I have a pretty generic kind of a skeleton for an SDC file over here. And it has three parts. It has the clocks, it has the IO constraints, and the DRV constraints. And we'll start with the create clocks command, which is the most important. And really I have this create clock minus period minus name, and which port it's going to be created on. Now, since I made this kind of generic, in your defines file, we're going to provide a list of clocks so you can have more than one. If I have several clocks, I'm going to give a clock port list for each of those clocks, and I'm going to give a period for each of those. So if I use this for each with three parts, it's going to iterate together over the three lists. So it's going to take the first member of this list, the first member of this list, and the first member of this list, and create a clock for the three of them. And then it's going to take the second member, and it's going to create a clock for the three of them, and so forth. I also put on clock uncertainty for the clock that I made to add some sort of jitter. If I'm in synthesis, I also want to set that both the clocks and the resets are both ideal networks, so I won't start buffering them right now during synthesis. Next, I go to the IO constraints. So there I have my set input delay, And I just did something very generic. It's not what you're actually going to do, but it's to set input delay. It's going to take some sort of a global parameter of input delay and put it on all the inputs except for the clock port. Now, again, this is not something that I'm going to do in such a generic way. I'm going to get from my top level design, whoever it is, what the budget of each of the ports are, and then I'm going to set my input delays or my output delays, or as I have explained during the lecture, prefer max delays. I am going to do that single-handedly for each and every one of the clock ports or collections of clocks. But here, right now, I'm just putting some sort of a global on all the inputs and a global on all the outputs. I crossed out this set max delay from inputs to outputs because I don't have any in-out ports, in-out paths in this design, and it would have given me some warnings in my timing linting that I'm going to do. The next thing is we need to model the inputs and the outputs. So how am I going to do that? I'm going to find some sort of a value for my load, and that's going to be tech SDC load value. I couldn't have set this up inside my libraries because I needed to have my design read in first. But what it's going to do here, it's going to look at the pin of some sort of a standard cell that we set as the load pin, maybe a mid-sized inverter or something like that. It's going to grab the capacitance out of it, and it's going to take the first member of that, and that is going to provide us with some sort of a load value in picofarad, which then I can do set load and put that on all the outputs. So all the outputs are going to see this load, which is just the input capacitance of some standard cell that I have in my library. Okay, I need to put input transition or driving cell, so I can define some sort of ideal input transition, or I can set a driving cell, which is some sort of a lib cell that is going to be used as a driving cell, which is also defined inside my library, my standard cell library definitions. I can also set some max fan out, max transition, max capacitance, and so forth. Usually you don't really have to do this because it is going to be set inside our lib files by default. So at this point, you may want to write out your design just to have it saved after elaboration if that took a long time. You don't necessarily have to, but every time you want to have a checkpoint where you can reload your design, you use this write design. There's also write db. You can use either of them to save your design. There is this option of reading in a floor plan, so I'm going to read my floor plan in over here with a read def command and then a check floor plan, but I'm not providing a floor plan at this point, so I'm going to skip this part. Okay, we also can do something now. We can define cost groups. So cost groups are the reg to reg, into reg, reg to out, into out groups of paths. We may want to make other groups of paths. We couldn't do it before because we didn't have our actual design handles. So now we can do it. So how do we do it? We have a command define cost group, and then we use this command path group from all registers to all registers. We'll make a reg to reg type of a group, and we give it a certain analysis view. So this is actually done inside one of the procedures that I already made up to do these, but I can do other specific ones. If I have some paths that I want to pay attention to specially or something like that, I can do it. And I'm going straight into the synthesis. So we're going to do EnICS start stage synthesis. And the first thing I'm going to do is define cost groups. So there is no command in Genus for some reason for creating the default cost groups reg to reg, into reg, reg to out, and into out. So I wrote a little procedure that does it, and it's called EnICS default cost groups, and it creates all of them for me. And then I can run this EnICS report timing, which is going to provide timing reports that are going to be written out into my reports directory. So I'm just running that. And in my reports directory now, I will have a directory called synthesis. And in that, I have timing paths now for reg to reg, which I can go and look over for reg to out, into reg, and into out is going to be empty because there are no paths in there. So I can already look at the timing paths, but since I haven't mapped anything to any standard cells, these are unmapped. You see flip-flops, NORs, NANDs, and so forth, but it shows me some sort of first way of looking at my timing. Okay, it's time to synthesize. So our design is elaborated, and that means that we've inferred all our registers. Our combinatorial logic is described with Boolean primitives. The IPs are bound to their lib files, and we've defined the optimization constraints. So we're ready to go and synthesize. And so we start with generic optimization, which optimizes data path components. In other words, it takes like a multiply and uses a Booth multiplier or a Wallace multiplier or something like that that is provided in chipware or designware environment. It's going to insert clock gates. So for low power, it's going to use clock gates. It's going to implement mux structures, which can be made in all kinds of different ways. So how am I going to do that? I'm going to set a DB of the entire tool, which is called syn generic effort. So syn generic is going to be our generic synthesis command, and I can say, let's say I want to put medium effort into it, and that's a trade-off of runtime versus what the results are. Okay, and then I run syn generic minus create floor plan minus physical, and that's actually going to take and assume that there's this square floor plan, and then it can do physical synthesis. Otherwise, I would just run syn generic. Okay, following this, we're still not mapped to library cells. So if we look, we'll see that we just have these generic kind of NAND and NOR and OR and flip-flops and so forth, but they're not actual standard cells from the library. And now it is time to synthesize. Well, first I have some settings, for example, on clock gating that I want to put clock gate when I have at least 8 flops that share the same enable, and I'm going to use a latch for that from the standard cell library, so I can grab these. There are other DB settings that I may not have gone over all of them, but there are a lot of them, so you may run into them. Okay, there's another message over here that I have these scan flip-flops, which are sometimes used for general type of synthesis, and then they cause problems in the place and route tool. So I have this don't use by setting .avoid true. That's a type of a don't use on the scan cells, so I don't use them to map standard logic to them. And now going over to synthesis, basically it is 3 stages: syn generic, syn map, and then syn opt. And so I can either do it with the floor plan or without a floor plan. We're going to be without the floor plan. First, I'll set my settings over here for the effort. So there's generic effort, map effort, opt spatial effort, and there's design power effort. There's all kinds of other ones too. So I'm going to set those ones for right now. They all have defaults if I don't set them, of course. Okay. And I will then read this in. It's actually, I'll do it one by one. So I'm going to do syn generic. And I add this minus create floor plan minus physical, which is going to create this default square floor plan with 0.7 utilization. And then it's going to do a physical generic floor planning. Okay, so let's see what happens there. So it's running that, and it's running it pretty fast because it's a tiny design. And it's going to run through here and eventually finish. So that ran, and if it took a few seconds, it would run much faster if I hadn't used the physical part. And you can look through all of the things that it was saying over here. Again, at this small design, it's not going to show us too much. All it did right now is it synthesized to generic, so it used all kinds of data path objects and things like that. It didn't yet map to standard cells. So as an example, I can look at what kind of chipwares or designwares it used using the report data path report. So it tells us that we have inferred components. It used this, I guess it's a subtractor, very fast decrement unsigned 4x1 and an incrementer. And it tells us what the area is and how much of the percentage total and so forth. So I can look at the types of different data path chipware type things it used. But if I send a report timing over here, I still see that I am unmapped. So I still have these generic type of cells. I don't have real cells. I still have unmapped cells. Getting standard cells from the library only happens during technology mapping, and then I can do post-mapping optimization. So it's actually pretty simple in this case. I have all kinds of, again, DBs that can control all kinds of things. The main one is syn map effort, and then I do syn map, and I can add the minus physical to have it do physical synthesis. Okay, and now when we go and look at the database in whichever way we want to, we can see that they're connected to actual standard cells. So I can do something like getDB, look at some instance, the state reg instance, and I can do .base cell, and it will tell me what standard cell it is connected to. Okay, and then we can go on to post-synthesis optimization. So I can set the optimization effort and run synopt. And if I use the minus spatial, again, it will do this physical synthesis using Cadence iSpatial. And now I can actually go over to the technology mapping stage. So I'm going to do synmap minus physical. And after a while, this finished. And I, again, can go through the different logs over here, or look through the log file and see what it did. It gives all kinds of info that at this point I'm not going to look deeply at, but maybe when we go through a bigger design that has actual timing problems, we will look through the log file over here, but usually we just look at the results using report timing or so forth. So I can really run over here, an EnICS report timing, and it will create reports about that, which is going to be under technology mapping reports. Okay, and finally, I'm going to go to post-synthesis optimization. So and that's going to be using this iSpatial, which is Cadence's physical synthesis tool. Here's the type of command that I tend to suppress, but I haven't yet. As we see, it has this tickle command 513. The software could not find a matching object of a specified type. That's something that I would really like to get rid of. So I suppress message on it. And finally, it finished, and that took quite a while because of this physical synthesis, which opened Innovus and ran this iSpatial and so forth. So if I had run it without the physical synthesis, it probably would have finished much faster. Finally, when that finishes, we can look at the timing reports and see how we met timing, and there's a lot to say about timing reports. So now that I am post-synthesis optimization, I can do some sort of report timing, and we can do lots of types of report timing. And I look at that, and my report timing shows my worst path, and it tells me that my path is met with a lot of positive slack. It's a setup check that the pin that it ends at is over here, right? It's using the worst case analysis view. It's on the clock group. It starts at the ACT signal, rising edge of the ACT signal. It ends at the state reg 1D, so it's an into reg path, okay? And we see that I gave it 6 nanoseconds of time to run it. It has setup time, uncertainty, required time, and so forth. And it shows me the path that it goes through these cells. And the cells are different types of cells over here. And I see that's what I get. So there's lots of this type of stuff about report timing. And I think we'll look at it later on during Innovus to a much deeper state. So other than timing reports, we have a lot of other reports. One of them would be report area that summarizes the area of each component of the design. Report gates will generate a report of all library cells. Report QOR is a general report of various design data. And once we've done that, we can export our design, which is write design. That generates all the files needed to reload the session in Genus. If I add the minus Innovus minus DB flags, it will enable us to load the design in Innovus Tempus Voltus. That has to load Innovus, so you need the license for it. It also takes a bit longer to do. Okay, write netlist will write out a structural Verilog netlist. Write SDF will write out the timing data for back annotation simulation. So other reports that I have are report area, which is going to show me, just what the standard cells area are and the total area of them and so forth. I can do a report gates. Report gates is going to give me like each of the gates that's used, how many instances, what their area is, and so forth. Report clock gating is going to show how much clock gating I was able to use. So it tells me how many total gated instances and so forth there are. Report design rules is going to tell me if I have any design rule violations. I don't have any max transition, max capacitance, or max fan out violations. Report DP, we saw before what types of data path things I'm using. And finally, report QRR, which is going to be like a whole bunch of stuff that it's going to tell me about. So it tells me instance counts and area and power and so forth and so on. So that's all kinds of reports that I am going to get. So the final part is exporting the design. And what we're going to have over here is we're going to first export the design database. Okay, so we are going to write out the design, and that's going to run quite a bit. So that took a while to finish, and you see it says ending Innovus, and the reason is because I use this minus Innovus minus DB option because I'm going to want to load my design into Voltus, and I need that or else it doesn't provide all of the files that I need for that. Next, I'm going to write out my net list. So it's going to write out my post-synthesis net list. Okay, and when I go and I look at what this actual variable is, so I see that it is export sm.postsyn.v. So let's go over there and we go to export sm.postsyn.v. And now I see that I do have standard cells from the library, and I'm no more using generics. The final thing that I'm going to export is the SDF files. So these are this is timing information, which I'll need for back annotation simulation. So I'm going to write that out. And I get an SDF file in under my export directory. So I see sm postsyn SDF. To summarize this demo, we saw how to run synthesis with Cadence Genus. We set up our run by defining variables inside our article arrays. We defined our MMMC file to set up our analysis views. We read in our RTL. We read in our left files to support physical synthesis. We elaborated our design. We initialized our design and checked that our SDC definitions were okay. We ran generic synthesis, technology mapping, and optimization. And finally, we looked through our reports and exported our design. In between, we also saw the Genus virtual directory structure, used collections, and learned how to access database objects with getDB and setDB. Now we're ready to go on to gate-level simulation and physical implementation.